Hey, Rani here. Shall we make a game? Now, last time we had this bug where this would kind of fall off the nav mesh, and I realized what it was. It was something incredibly dumb. It wasn't actually in the code running at runtime, it's in the code converting the OBJ file to code. So you can see how we have all these kind of like normals on the edges. Basically, they're the planes you have to cross to get from one triangle to the next or to reach the wall. Well, it turned out that I had that. So one of these normals, A, wasn't a normal, and B, was pointing in basically a borderline random direction. So now we have some sliding collision working. It seems to be working very nicely, actually. We need to start thinking about what kind of has to come next for us to work. So one thing is that we need to be able to, when the player clicks on a point in the scene, like say here, we need to be able to turn that into a point in 3D space. And wherever the mouse cursor happens to land, we need to be able to retrieve that information. We then need to use that to set the destination of the protagonist. And we then need to implement kind of like a roaming feature. So the way this is going to work is it's going to like look at the, let me just bring this back in, say the protagonist is here. It would check whether there's basically a straight line between where it is and the destination. If so, it walks there. Otherwise, it then needs to do kind of like a floodful search. It needs to start here. Okay, not there, not there. Ah, there it is. We found our nav mesh tile. And then go, well, that means I crossed this edge because it's the next thing in the sequence. That's another thing. For that, we need to know if there's, we need a function for direct line of sight. And the other thing that we need to know is we need some feedback for when we're crossing edges, because at the moment we don't really have great feedback. At least for this game, it's going to, I think we currently return a, where is it? Yeah, we currently return just basically a type indicating whether it crossed, say, an edge, or whether it collided with the edges of the navigation mesh. That kind of works, but it's not very good. Means that if we want like sound effects and hitting walls, or wanted like that kind of thing, can't really do them. We want like an animation that play when you land on the ground. Now, this stuff isn't going to factor into this particular game, but you couldn't do it with that existing system. All the math is there. It's just that we haven't plugged it into everything else very intelligently yet. But for now, we're going to work on these other things. So I guess the most pressing thing is to find the kind of like the location of the mouse cursor in the scene. So if I go to the scripts, sorry, it's scenario, movie theater, there we go. So we currently have this bit where if this protagonist, I'm going to make a new entity for a target. And just going to make a new entity for that and put a mesh component on it, nice and simple. And then we're going to need we have these callbacks on the, where's the world? There it is. Yes, at the moment we have all these callbacks, not using any of them. Don't remember what order they're in, let's have a look. Hover, unhover, activate, deactivate, click, so we want the last one. So when we click on this, we basically want to get the information about where we clicked on and kind of use it. So if let's go type something in there. Let's go get the type that we're trying to implement. That's pretty simple. Yeah, so at the moment, we'll have no information in here at all about where we actually clicked in the scene. It's good enough for, say, buttons and stuff, because we only need to know which one we clicked, not where we clicked them. But we need the ability to track exactly where you've clicked them. So let's have a look in selectable component. So yeah, I think there was a thing in here for sampling. Yeah, there's a sample callback. So at the moment, this just, I think it just returns, yeah, it returns the distance. Now, I believe it is actually possible to go from a distance to a world space coordinate, but A, it's kind of complicated, and some things are a bit more complex than that, such as the 2D objects, like those kind of need to sort of project onto a plane, I guess. So I guess what we actually need in there is Oh, yeah, we can actually do. It's a bit cheeky. We can actually have a second sample callback because like 90% of the time, we're not going to need the information of exactly where it was intersected. And we could probably save some performance. But that would then mean having to implement like, the triangle intersection twice. Do I want to do that? The answer is no. Well, in here, I think we're already like interpolating the depth, I think. Yeah, we're passing in the depth. Okay, so we don't actually have the world space coordinates in here. I don't think we do anyway. Yeah, that's right. We only have the I have to think about a good way of doing this because I'm not certain on that. So the only thing that I think we actually need is the inverse view matrix, which I think should be possible to derive pretty easily. I mean, if we go to the camera is the only place we need to store this, and yeah, we can pretty much just store it in here. Ooh, let's keep this. So yeah, so step one is, let's just save that as well. Go to the camera, and we're going to add a new function here to turn a, oh, it's not just a depth though, it's also a screen coordinate. I guess. I'm thinking, and it does hurt. How am I going to do this? How am I going to do this? So I guess what I could do is I could I think the depth values run from -1 to 1. So yeah, if we can basically extract the frustum, the sort of camera, let me get the let me get Sprite up and kind of explain. So the idea is that if you've got your sort of camera, right, at, oh, is it doing this again? Oh, that's not good. Yeah, if you've got your camera, it's basically almost kind of represented by what's known as a frustum, I think it's called, or a frustum, I'm not sure which. And it's almost kind of like a square-based pyramid, except the top has been truncated, right? So this is the camera, this is where it can see. So one of the things is, right, when you've actually transformed all your vertices into what they call clip space, it's basically a coordinate inside this sort of frustum. So, you know, x minus 1 to x1, y1 to y minus 1, and same goes for z, although I think it might be backwards, just to be as confusing as possible. I think negative z is further away. So, if we know the depth, we have, if we know the depth, we have, you know, where it is along this axis, and we know where it is along these two axes because we have the screen coordinate, right? We know where the mouse is. So if we can basically reverse the whole pipeline, we can go from knowing the depth, knowing the screen coordinate, to knowing exactly where it is in the world. Testing this is going to be fun. Okay, so camera, clip to world, I guess that would do. Okay, calculates the location of a point in 3D space based upon its clipped space coordinates. Can't type. Location of the point in clip space. Oh, I just cannot type tonight. What on earth is happening? Okay, that function will be very, very, very useful if we can get it to work. So things like 2D surfaces are going to be a bit weird, but I'll probably just not use it for those. Okay, so we don't currently store this anywhere. We just basically apply it and then move on. Um, hmm. Hmm. So I think about the best way of doing this. Because what we basically have is what we basically currently have, we have a matrix which takes you from this space into this space, right? It takes you from world into clip space, and we need to go from clip into world. And there's not really a simple way of just inverting a matrix. I kind of misremembered that. If we can figure out, yeah, if we can figure out basically kind of like the sort of normal of this, right? And we can figure out kind of like the span of this and the span of this. We can basically just, yeah, we can figure these directions as well, which is basically what the matrix is going to do for us. How do I compute that matrix though? Let's ask Google. Clip to world. How? No, not hoi. Avoid Unity because we're trying to avoid copying Unity too much. Getting world position from a depth buffer value. Okay, what they do? Because this is inside a shader. Oh, so they've got an inverse view matrix. That'd be kind of handy to have, honestly. Hmm. Yeah, maybe it's a camera-based approach isn't the right way to do it. As much as I kind of like want to have that simple solution, I don't think it's quite the right way to do it. Let's close this as well. So what we can do is go into a triangle function, and where we're sampling it, we can make it instead return, well, we can make it output. Output the world coordinate. That'll work. But this is a lot of wasted performance. There's a lot of like wasted kind of CPU time, you know, calculating these world coordinates, and we're going to be throwing them away 90% of the time. There has to be a simple way to go from clip to world. What if instead of distance, it's output like world coordinates? That wouldn't be great. You'd have to be doing a distance calculation for everything in the scene at that point. Okay, so what we can probably do is just put this back in and put this back in. And if we go to this sort of camera callback, we can make an output and inverse of both of these. Right, and then we can probably, so what I was thinking about doing anyway is we currently have that function that generates all these matrices, and we have one that does the inverse. And I'm thinking about just combining them because they're kind of always going to be used together eventually. Okay, that's going to break everything, but that's fine. Oh, hang on, but what about this? This gets complicated. Because we need to apply camera shake. That's okay though, because when we actually adjust this matrix function a bit, we can make it output the inverse and then apply both of them. Yeah, that'll work. Okay, so there should be in here, we've got model and view, so we can get rid of both of these. I think. Oh, the view one doesn't support scaling. Okay, all right. How similar are they? Is it going to be trivial to put one in the other? I don't remember how this works. It's been years since I've written this, basically. Ah! Yeah, okay. I mean, how often am I going to be scaling things anyway? Probably not very often, especially not cameras. Do I just drop the scale argument? I mean, that kind of feels a bit wrong, but I guess I could. Thinking about it now, I am going to need the scale argument. Ah! I've kind of painted myself into a corner with my architecture here. Ah. Okay, how am I gonna work around this? How am I gonna fix this? So there's two main approaches I can use here. I can either maybe tackle a different problem for now and I'll just think about this and come back to it later. That seems like a reasonable approach here. Okay, so I'm not gonna do that just yet, or that. So I guess we could do this, the sort of method for determining if there's a direct line of sight over the nav mesh to a destination. So it's basically a kind of like a sticky collision check, I suppose. That's now one of the things that's special about that is it needs to not consider the floor, which is a bit weird, but it means so that, like, to give an example of why that's important, if you say looking from side on here, if you had that, right, if you had like a hill, the guy standing here and he wants to get over here, even though there's not line of sight, there's kind of like line of travel, which I think is maybe a better term for it. So that's what we're going to call it. So do we have the bool header? No. It just occurs to me this bool type doesn't have a T suffix on it. Interesting. Okay, so it's going to determine whether whether it is possible to travel between 2 points on a navigation mesh in a straight line without encountering a wall. Does not consider the surface not a line of sight check. And we're going to take it to here. We're going to take in a navigation mesh and our origin destination. Now, I don't know whether it's going to be useful at any time to have the results, because you're never going to be using it for that. It's just it's kind of like a line. It's almost like a line of sight check, but not line of sight. So I'm not going to put that on there until I need it. It'd be easier to put it on later on. And again, this is going to be an iterative thing, so we're going to be going over edges. Oh, I'm regretting commenting out or deleting all of the code in the advanced function for debugging stuff. Okay, we'll deal with it. We'll deal with it. We'll figure out we don't actually need to do that. What we do need, though, is we need the index of the triangle that we're currently in. Oh, it'd probably help if I actually documented all this stuff as well. Look at the location the travel would start from. Location the travel would head towards. And we return when there is line of sight, travel, true, otherwise false. Okay, there we go. And copy this over to here. Just because we changed it a bit. There we go. All right, so this is going to be dead simple. Haven't we heard that a few times? We're going to iterate through. Take that, I think, though. Yeah, we're going to iterate through and keep going until we either land on the triangle containing the destination. Oh, that's a good point, actually. We need to know not only do we need to know where we're going, we need to know where. Sorry, we need to know which triangle we're going from and which triangle we're going to, and then where in that triangle, because each triangle is actually a kind of like a, just to kind of explain it. The triangles aren't actually just surfaces, they also have volumes, so it look more like this. So if you say had, for the sake of argument, something like this, if you were just checking points, right, bear in mind that this means that you have kind of like overlapping volumes like that. In theory, you'd be able to travel directly to there, but what if you were actually trying to travel to there? You know, in theory, you'd be inside the volume that you're trying to get to, but that doesn't really matter. So we need to know exactly which triangle we're trying to get to as well. Okay, that should be good. And we're going to start at the origin, and then we're going to have a maximum number of iterations. Probably set this a bit higher, because like whereas the previous sliding collision function is kind of like built for so if it happens every frame, this is something that'll be happening infrequently and could be crossing the entire map. Check. Nope. Good. Okay. Checking. Okay, good. Right, okay. So first of all, we need to check at the very beginning, are we currently in the right triangle? If so, return true, as we've reached our destination. You have reached your destination. Otherwise, we need to then look at our current triangle, and we need to basically determine which of the edges we're going to hit first. So if we're kind of in our sort of triangle like this, we could have like this ray coming in like this, and we need to know which of these edges we're going to hit first. So just thinking about this from kind of like a So we do want the same kind of edge tolerance system we have in this, where the triangle is basically almost kind of like double skinned. And whenever you say like collide with this edge, it actually kind of puts you onto this edge. We kind of want to take that tolerance into account in here. So I might actually put this into a static constant just so we can use it in both. Okay. So at that point, yeah, we need to, so we know which triangle we're in. We can now get the detail on the triangle. And now we need to compare. We need to compare both the origin and the destination to these planes and figure out which ones it's passing through and at which times. And then whichever one it hits first is the one that we're kind of like most interested in, I think. Because like say it did that. Technically it crossed both planes there and there. But we're only really interested in this one. This is the one where it really crossed into the neighbours. So let's just make a bit of temporary memory to hold the kind of differences. If I subtract, so at this point we're subtracting our kind of destination point from one of the corners, then going to do a dot product and determine if it crossed the line. So we need to actually extract the corners of the triangle. That'd be a good idea. What do they call these? Vertex locations. There we go. That makes way too much sense. And we also need to take we take both the origin and destination difference. So yeah, sorry, just taking a moment to think about something. So I want to take the origin less b. It's got 3 x's, and that's the origin difference b. destination difference. So one of the things I want to be quite careful with here is that if I say have a pair of triangles like this, and we've got like a line that runs basically all the way through it, we don't want rounding errors to be constantly flipping us from one triangle to the other. We want to basically just pick a side and stick with it, even if sliding collision doesn't quite agree with it. So in that case, we actually want to be over a threshold before we consider ourselves crossing it. So this point we can do a simple origin AB distance. It's dot product, isn't it? Yep. And then what do we call this? Edge exit normals. That's the one, yeah. Edge exit normal AB. So if the AB distance is yeah, so if we started within the kind of like expanded triangle and oops. Yeah, so if we start within the triangle, we then work out whether the destination has crossed the line. If it has, that's when we start sort of working with it. Try to think if there's any reason I wouldn't want to do that. No, not really. Yeah, that's fine. Or a random window could just open for no reason in the middle of me typing. That's great. Thanks, Windows. Okay. So at this point, we know that we were previously inside the line and we've now crossed it. Is there ever going to be a case where I think is there ever going to be a case where we cross two edges and we need to pick one that isn't the closest? But no, I don't think that is the case. Right, so we next up need to, hang on a second, thinking about this. We next up need to, oh God. Way too tired to be doing this. Calculating the closest distance, that's it, yeah. So the way we calculate the distance is, let me just remember how this worked. So what we have at this point, we have a line, we have a start and an end point, and we have the distance this way, and we have the distance this way. So let's say that for the sake of argument, we're 3 inside, because we're going that way, and then 2 outside. That means that we want this to happen at 0.6, but it would actually be -3 inside. Closest distance. And we don't actually need to initialize this variable. Okay, so at that point, it would be the origin distance, which is going to be -3, divided by origin distance, take the destination distance. I think I've written that code about 5 times, and every time it feels kind of weird. Okay, so next up, we're going to do the same thing for, actually, I want to do both the origin and destination at once, and we're checking multiple edges. And then we'll do the same thing for edge BC. And then we'll do it once more for edge CA. And that one we can skip one of the calculations. Okay, let's collect these as well while we're here. Still using the old type names. What am I doing? Okay, there we go. Oh yeah, I also need to tell it how many edges, how many sides there are to this. How many dimensions we're working in. Keep forgetting I have to do that. All right, okay. There's another a slight edit we need to make to this as well, which is that if we already have a neighbor, we have to check whether we're closer. And then we have to repeat this down here for this one. At which point we now know which edge, if any, we've crossed, and we now can do a switch case down here. So, neighbor. So if we didn't cross an edge, so I think how this would work. I guess we need to stop if we've crossed an edge because, well, if we're not crossed an edge, because at that point we don't necessarily know where to go. We should probably flood fill. Yep, that's fine. Next thing is if we did cross an edge, we need to check whether that edge actually goes anywhere, and if it doesn't, that's when we return false. So, okay, so now we have the index of the triangle we'll likely be crossing over into. We need to check, is that none? Because if it is, that means we've hit a wall. Otherwise, we move on to that triangle. And then we continue. And then if we run out of iterations, I'm thinking that could either mean that, yes, we just haven't reached it, or it could mean, no, it's too far away. So I'm going to assume it means no, it's too far away. That function might work. Let's, can't think of a good way of testing it really. Not in a visual way. I guess we just kind of leave it at that. That's at least one of our kind of to-dos sorted. Next thing to do is actually to implement this flood fill. A way of kind of like determining the next edge we need to cross. So again, let's go back to the drawing board, and can you imagine if you got, say, nav mesh like this. If we're in, say, this triangle here, we know, and we're trying to get to this triangle, then we're basically going to start here, we're going to try crossing this edge, try crossing this edge, try crossing this edge. And that's very simple. That's, all well and good in the trivial case, but what about this? Because then there's actually multiple routes. And if you're not careful, you could actually say go around here and then loop back onto yourself. How are we going to deal with that? So, especially in a system where we're not allocating memory, how are we going to deal with that? So I guess, if we're doing like because the simplest, crudest way of doing it would be to do it static. I've drawn like a bird face, haven't I? Oops. Give it a little wing here. Because the simplest, crudest way to do this would be to have like a lookup table, right? Which is like, I'm here, I'm trying to get here, how do I get there? The problem with that is it actually like grows exponentially. So if you had, say, 100 triangles, which is, actually let's go for 1,000. 1,000 is pretty reasonable. And you then wanted to have, a lookup table of every triangle goes to every one. That is 1 million entries. That's a megabyte of memory occupied for a 1,000 triangle nav mesh, which isn't going to be that much in the grand scheme of things. Now, we could actually cut this down a bit, like, because there's only 4 options, which are A, B, C, or none. You could, in theory, pack that into 2 bits. So you could actually divide this by 4 and fit that to 250 kilobytes. That's still 250 kilobytes of data for a nav mesh. So I don't think we have enough agents that's really kind of worthwhile doing. So what can we do? Well, I guess a really crude way of doing it, right, would be to basically just have, we'd have kind of like a rough estimate of the distance between 2 edges, right? We'd probably have this cached because we're hitting it so often. But say, we have inside a triangle, we'd have kind of like a various sort of edges like this, and we'd have kind of like pre-cached measurements for these edges. And then we'd have basically just an array of all the triangles, for each triangle in this nav mesh, we'd have basically the distance it took to get to it. We'd pre-initialize that to infinity. And the idea is that you'd, that array would contain both the distance we took to get there and the edge we crossed to get there. So that, that means that actually not even that. It wouldn't need the edge we crossed to get there. We just need the distance. And then we work all the way up to there, and then we just kind of like do a depth first search. And whenever we get to a triangle and we find a quicker way of getting there, actually, I get nastier when it comes to kind of like propagating. Because if we find a faster way to a triangle, right? Let's say that, we went for the worst case scenario. Let's get change color here. Let's say that we started here and then we'd gone all the way around here, and obviously that's quite a long way to get to here. At which point, we said that this is, I don't know, 30 meters away from our start or whatever. And then, we iterate all the way back around to here, and we iterate around here, and we get to here, and we now know that we got to here in only 20, for example. Well, then we need to reflood fill into all of these because now, you know, we've found a quicker way of getting to those, and that route might now make sense. How long is it going to take to actually do that kind of flood fill? Because, again, if we were talking about enough memory for, say, like 100,000 combinations, I don't think we're looking at the same amount, but like we're probably looking pretty close, right? Especially if we, you know, happen to take the worst route first. I'm just saying we could do to speed that up. Like if we could pre-sort the array, so we're taking, you know, what would typically be the shortest routes first. I don't know. That has to be possible, but it'd be a huge amount of complexity. I mean, it might even be that we find a route and then stick with it, even if it's not optimal. I guess pathfinding is going to be pretty infrequent in this. Let's have a look. What kind of yeah, what kind of? Cause I kind of had like my sort of take on it. What kind of functionality do people use to do this? Pathfinding within one of these polygons. Yeah, transfer. Okay. Graph search such as A sharp. Now I've heard of A sharp, but I don't know anything about it. Practical drawback is OBD. It stores all generated nodes in memory. Okay, so they're talking about the exact kind of problems I'm kind of experiencing here. So I think this is the one that kind of like... Right, okay. I'm never going to have this many like nodes in my nav mesh, but yeah. Are they kind of like weighting this so they're heading in the general direction of the destination? Because if so, that's pretty clever. Right, okay, that's right. Yeah, they're basically heading in the general direction of the target and then kind of routing their way around any blockages until they find a good path. That's pretty clever. I'd never really looked into how that actually worked before. I did see that Unreal Engine 5 has the ability to dynamically edit nav meshes, which is just insane. I can't believe that someone actually pulled that off. Interesting. I guess the question is, am I looking for the best route or am I looking for a route? Whilst we have it, let's have a look at some more algorithms, shall we? So I might go for my approach of storing the distance. So that means I'm going to have a limit on the size of a nav mesh. That's fine. That'll probably do. And we're going to have to add a thing in here storing the kind of distances between the triangle edges. Just so I'm not having to calculate, and not just so I'm just not having to do a bunch of square roots every time. Here it is. So triangle. The average distances between edge pairs. There we go. AB and BC. Yep. And then BC and CA, CA and AB. And we need to calculate that at some point. That's going into an Object-C thing. Look at all this code I'm writing today and just not bothering to test. Isn't it wonderful? So I might add a new type for a navigation mesh neighbor ID. And then we need an option for none. Annoyingly, it's going to be non-zero. At long last, we'll be navigating on a navigation mesh. It's been so long. So we're going to give it a index, so an origin, a destination triangle, and then we're going to return the neighbor you should cross to get there. Determines the route to take. Determines the next neighbor. Hang on, determines the next edge to cross. So it's not actually a neighbor, it's actually an edge. Okay, so the next edge to cross to navigate between two triangles of a navigation mesh. Okay, and now we what was it like to say? We draw the rest of the owl. So the first thing we need to do is we need to get the number of triangles out. Yep. And we're actually not going to be using the triangles themselves. We're just going. Oh, actually no, we are. We're going to be using the edge distances. Okay. Yeah, so where do we put these edge distances? We are going to move these into kind of here. And I think that's us done for today. I'm flagging so hard. I'm just not even going to try and go much further than that. If you watch this, you have way more patience than I do. Thank you for watching. Have a great weekend.